Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Alex, I need to tell you about the strangest paradox I've seen in infrastructure. Kubernetes has 92% market share in container orchestration, basically total dominance. But get this, 88% of organizations using it report year-over-year cost increases, 75% say complexity is blocking adoption, and 25% are planning to shrink their deployments in the next year.
Wait, hold on. That doesn't make sense. How can something be both the industry standard and simultaneously failing for nearly everyone using it?
Exactly. And that's what we're digging into today, because the answer isn't Kubernetes is bad. It's way more interesting than that. This is about the gap between market dominance and actual satisfaction.
Okay, so let's start with the cost piece. 88% reporting cost increases. That's not a minority. That's everyone.
Right. And it gets worse. Cost has overtaken skills and security as the #1 challenge, now sitting at 42%. The CNCF FinOps microsurvey found that 49% of organizations saw their cloud spending increase after Kubernetes adoption. Only 24% achieved savings. The math wasn't mathing.
What's driving that? Is it just compute costs spiraling out of control?
Actually, 70% cite over-provisioning as the top cause of Kubernetes overspend. Teams request resources just in case, cluster autoscalers struggle with bursty workloads, and nobody has clear visibility into which pods are actually using their allocated CPU and memory. You're paying for capacity that sits idle.
Yeah, I've seen that pattern. What's a good example?
In the Pockets Cloud team operated 50 microservices on Kubernetes before migrating to AWS ECS. Post-migration, they observed a drop in database connections. Their ECS pods required fewer instances than the Kubernetes setup. The first invoice post-migration was cheaper on day one.
That's significant. So they did the migration and immediately saved money, not eventually after optimization.
Exactly. But here's what really gets me. Teams consistently underestimate Kubernetes costs by a factor of 3 to 5 times when making adoption decisions.
3 to 5 times. Walk me through that math.
They calculate compute costs, EC2 instances, persistent volumes, load balancers, but miss the hidden expenses. First, human capital. You need 3 to 15 full-time platform engineers for production. At a $150,000 average salary, that's $450,000 to $2.25 million annually before benefits and overhead.
And that's just the people.
Right. Second, training and ramp-up. 6-month minimum for engineers to become productive with Kubernetes. Not hello world time. 6 months to independently debug production incidents and contribute to platform improvements. Third, tool sprawl. Monitoring with Prometheus and Grafana, logging with Elasticsearch or Loki, security with Falco and OPA, GitOps with Argo CD or Flux, service mesh with Istio or Linkerd, secrets management with External Secrets Operator, cost management with KubeCost. Each tool adds licensing costs, integration complexity, and operational overhead.
That's a lot of surface area to maintain.
And fourth, opportunity cost. Platform engineers maintaining Kubernetes instead of building features that drive revenue. According to Spectro Cloud's 2024 report, nearly 2/3 of businesses report their Kubernetes total cost of ownership grew in the past year, and 2/3 lack visibility into future cost projections.
So they know it's getting more expensive, but they can't predict by how much.
Exactly. Let me give you a real example. A mid-sized SaaS company with 30 microservices made a decision in 2023 to adopt Kubernetes. 18 months and 3 full-time engineers later, they ripped it out entirely and migrated to AWS ECS. Their CTO told me, "We finally did the math. The Kubernetes cluster required constant EC2 maintenance, Helm chart updates, and monitoring overhead that ECS handles automatically." Their first ECS invoice was cheaper than their Kubernetes setup, and that's before accounting for the 3 FTEs they could redeploy to product work.
So if teams are missing costs by 3 to 5 times, what's driving the complexity that's blocking 75% of adopters? Because that stat is wild.
The CNCF landscape. 209 projects across categories like container runtimes, orchestration, service mesh, monitoring, logging, tracing, security, storage, and networking. This isn't a collection of complementary tools. It's a labyrinth of overlapping solutions, competing standards, and constant churn.
Analysis paralysis as a service.
Exactly. And it's not improving. Organizations report experiencing more challenges managing Kubernetes than the prior year, with more than double now regularly suffering issues with cluster operations compared to 2022. The maturity paradox. As Kubernetes matures as a technology, operational complexity increases.
I'm guessing there's a story behind this?
Platform team at a fintech startup spent 3 weeks evaluating service mesh options. Istio, Linkerd, Console Connect, AWS App Mesh. They prototyped Istio, hit complexity walls with multi-cluster federation, evaluated Linkerd's simpler model, then discovered their 30 services didn't actually need service mesh at all. The evaluation consumed 120 engineer hours with 0 value delivered.
Ouch! That's expensive education.
And it gets worse. The service mesh adoption rate is at 70%, but many teams adopt because everyone else is doing it, not because they have the 100+ services that justify service mesh complexity. Meanwhile, Helm adoption grew to 75% from 56% in 2023, which sounds good until you realize teams are adding layers of abstraction to manage Kubernetes complexity. But each layer adds its own learning curve and failure modes.
So you need to learn Helm templating, values files, release management, and rollback strategies on top of core Kubernetes concepts.
Exactly. And let's talk about the learning curve. Getting Kubernetes running takes 2 weeks. Operating Kubernetes at scale requires 3 to 15 full-time engineers ongoing. That's the difference between theory and production.
What does that learning curve actually cover?
9 domains of expertise. Core Kubernetes, pods, deployments, services, RBAC, container runtime, Docker versus Containerd, security scanning, networking, CNI plugins like Calico or Cilium, service discovery, DNS, storage, CSI drivers, volume snapshots, security, pod security standards, secrets management, observability, Prometheus, Loki, Jaeger, GitOps with Argo CD or Flux, service mesh, if you go that route, and platform engineering, developer experience, self-service, golden paths.
And certificates don't solve this.
Great question. A healthcare startup hired a Kubernetes expert with CKA certification. 3 months in, a production incident revealed they'd never actually operated Kubernetes at scale, only completed training exercises. The certification validated theoretical knowledge, not operational expertise. Recovery required escalating to a senior engineer who'd managed Kubernetes through multiple upgrade cycles.
So what are these engineers actually worth in the market?
Kubernetes engineers average $120,000 to $160,000 annually, according to Glassdoor 2025 data. Entry level with 1 to 3 years is $97,000. Senior with 8+ years is $172,791. The premium reflects scarcity of genuinely skilled practitioners who can operate Kubernetes in production, not just run kubectl apply.
And the multi-cluster reality compounds this, right?
The average Kubernetes adopter operates more than 20 clusters, with 50% running clusters across 4 environments: dev, staging, prod, disaster recovery. Each cluster multiplies operational burden, upgrades, security patches, certificate rotations, configuration drift.
This sounds like classic over-engineering, but worse.
It's cargo cult adoption. Listen to this. 25% of organizations expect to shrink their Kubernetes estates in the next year. After investing millions in adoption, training, and tooling, a quarter are planning to scale back.
The Netflix fallacy.
Exactly. Netflix runs on Kubernetes, therefore we should too. Netflix has 8,600+ microservices resources, billions of requests per day, multi-region active-active deployments. Your 30-service monolith in progress has different requirements. Reddit and Hacker News threads from 2024 through 2025 reveal a consensus emerging. Most startups don't have Netflix's problems. They have get customers and stay alive problems.
And the auto-scaling everyone adds.
Most B2B SaaS applications have predictable workloads. Morning ramp up, steady daytime traffic, evening decline, weekend quiet. Autoscaling provides minimal value when you can predict tomorrow's load within 10% accuracy. But everyone adds it because cloud-native architecture.
So if Kubernetes isn't universally optimal, when does it actually make sense? What's the heuristic?
Industry best practice has converged on the 200-node rule. Kubernetes makes sense above 200 nodes with complex orchestration needs that simpler tools can't handle.
Why 200?
Below that threshold, alternatives like Docker Swarm, HashiCorp Nomad, AWS ECS, or even good old VM orchestration with Ansible can handle container workloads with dramatically less complexity. Above 200 nodes, Kubernetes' sophisticated scheduling, resource management, and failure handling start justifying the operational overhead.
Walk me through the alternatives.
Docker Swarm, 10-minute setup versus 2-week Kubernetes learning curve, handles under 200 nodes. HashiCorp Nomad scales to 10,000 plus nodes in production with multi-workload support, containers, VMs, batch jobs, binaries, all in a single binary with zero external dependencies. AWS ECS provides AWS native integration with tight coupling to ALB, RDS, Secrets Manager. Google Cloud Run gets you to production in 15 minutes with serverless containers that autoscale to 0. And PaaS platforms like Fly.io, Railway, and Render cost $400 a month versus $150,000 a year for a Kubernetes team.
Let's talk actual numbers. What does the 5-year TCO look like?
Here's the math everyone skips. Kubernetes for production with 50 to 100 nodes, platform team of 5 FTEs times 150,000 equals 750,000 per year. Compute is 60 to 120,000 per year, depending on workload. Tools for monitoring, security, and GitOps for 40 to 80,000 per year. Training and ramp up is 50 to 100,000 per year. Total 900,000 to 1.05 million annually. 5-year TCO 4.5 to 5.25 million.
And the PaaS alternative?
Railway, Render, or Fly.io runs $400 to $1,200 a month in platform costs. You still need one platform engineer, but with reduced scope, so $150,000 per year. Total, $155,000 to $165,000 annually. 5-year TCO, $775,000 to $825,000.
So PaaS is 5 to 6 times cheaper over 5 years?
For that scale, yes, and that's being conservative. Now, at 500 nodes with 200 engineers, Kubernetes starts winning because PaaS per resource costs become prohibitive. But that's exactly the point. Match the tool to your actual scale, not your aspirational scale.
What's the most dramatic example you've seen?
37 Signals cloud repatriation. 2022, AWS spend was $3.2 million annually, running on EKS, EC2, and S3. They invested $700,000 in Dell servers, recouped during 2023 as contracts expired. They invested $1.5 million in tier storage arrays, 18 petabytes with $200,000 per year operational costs. Cloud bill reduced from $3.2 million to $1.3 million annually. Projected savings, $10 million plus over 5 years. Team expansion, 0 additional staff required.
Wait, they had the expertise to run their own data centers?
Exactly the point. They have an 8-person operations team with deep expertise and predictable workloads at scale. Not every company should follow them, but their case proves cloud and Kubernetes aren't universally optimal. They're tools with specific use cases.
So what should teams do this week?
3 things. First, calculate 5-year TCO honestly. Include 3 to 15 FTEs, training tools, opportunity cost. Use the 3 to 5 times multiplier for hidden costs you're missing. Second, measure actual utilization. If you're using less than 50% of your requested resources, that's over-provisioning, costing real money. Third, run a parallel proof of concept. Deploy one non-critical workload on Kubernetes plus your top alternative. Measure time to production, operational complexity, and actual costs. Let data decide, not ideology.
The backlash isn't about Kubernetes being bad, it's about doing the math.
Exactly. 92% market share coexists with 88% cost increases because teams adopted first, calculated later. The ones shrinking their deployments, they finally did the math and realized simpler infrastructure wins. Not because Kubernetes is wrong, but because it's the wrong tool for their specific scale and requirements.
Match the tool to the problem, not the hype cycle.
Now you're thinking like a platform engineer.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.